Alright. Did have a few days off from Haskell. One was intentional, the other one was unintentional. I just lost track of time. But we're back. And we're making our own modules. Right, we've looked at some cool modules so far, but how do we make our own module? Almost every programming language enables you to split your code up into several files, and Haskell is no different. When making programs, it is good practice to take functions and types that work towards a similar purpose and put them in a module. Sure. That way you can easily reuse those functions in other programs just by importing your module. That makes sense. Is that the logic why people do object-oriented programming? That you split it up into, instead of modules, you split it up into classes? I don't know object-oriented programming enough, so I don't know, but I could assume that there is some overlap in that type of thinking. Let's see how we can make our own modules by making a little module that provides some functions for calculating the volume and area of a few geometrical objects. We start by creating a file called geometry HS. Sorry. Wait. You know what? Let's go. Wait, why did that not work? OB? What is happening here? No, it did work. Weird. How much room do we need? Like that, probably? For whatever reason, my window manager has stopped working. I can't... Oh, I'm pressing the wrong buttons. That's what's happening. I'm like, why isn't anything happening? I'm pressing the wrong buttons. It's not a window manager I'm trying to zoom in. I'm trying to zoom in the actual stuff here. Right, we make a file, right? Actually, we will probably write something in said file, so let's open the file. I'm not capitalizing the name of that. Do I have to? Geometry. Yeah. Modules. Yeah, they were capitalized, weren't they? We say that a module exports functions. What that means is when I import a module, I can use the function that it exports. Remember that. It can define functions that its functions call internally, but we can only see and use the one that it exports. Alright, so we don't export all our helper functions. We made one function that we can export, and that one uses helper functions, but those helper functions are just specific for said module. At the beginning of a module, we specify the module name. If we have a file called geometry.hs, then we should name our module geometry. Then we specify the functions that it exports, and after that we can start writing the functions. So we will start with this. Right, we have a module. Oh shit. We have a module. We call it geometry, which is a tuple. Alright. It's a tuple. Right. I'm just gonna copy paste this. Let's just copy paste this. I don't want to write that all out. Right, here we go. Sphere, volume, sphere, area, cube volume, cube area, cuboid. Is that a box that is not a cube? Is that called a cuboid in English? Sweet. Another crash, says NodeRunner. That's not sweet. It's that other thing. Ah. Right, where? Okay, so what is happening here is we define our module. This is our module. We have all these functions. And then, where, and then we will define our functions. We get, that's just the rest of the file, right? This where statement is probably about the rest of the file. As you can see, we'll be doing areas and volumes for spheres, cubes, and cuboids. Let's go ahead and define our functions then. Okay. You know what? This looks like math. You know how I feel about math. Feel like we just copy the math and we paste the math. There we go. I did math. Right. Pretty standard geometry right here. There are a few things to take note of though, because a cube is only a special case of a cuboid. But I thought we define its area and volume by treating it as a cuboid whose sides are all the same length. That's what I thought. I didn't know that it was called a cuboid in English. I learned something new. We also defined a helper function called rectangle area, which calculates a rectangle's area based on the lengths of its sides. It is rather trivial because it's just multiplication. Notice that we used it in our functions in the module named cuboid area and cuboid volume. Yeah, we made... Wait, what was that called? Rectangle area. Yeah, this is a helper function. That makes sense. Right, because in Haskell we split it up. Everything, we split it all up. We don't want a function that does two different things. Or that logic? Or is it just that we have rectangles in two different places? So instead it's easier to just call this helper function. Right, but we didn't export it, yeah, because we want our module to just present functions for dealing with three-dimensional objects. We used rectangle area, but we did not export it. When making a module, we usually export only those functions that act as a sort of interface to our module, so that the implementation is hidden. If someone is using our geometry module, they don't have to concern themselves with functions that we don't export. We can decide to change those functions completely or delete them in a newer version. We could delete rectangle area and just use multiplication instead. Exactly, yeah. I would probably go with the multiplication instead, since that's... And no one would mind because we weren't exporting them in the first place. They wouldn't even know. To use our module, we just do import geometry. And we can also do, I don't remember exactly the syntax for that, but we can import geometry, and like, I think we just put them in parentheses, so we could, right? Oh, I only need the cuboid area, so I don't need to import the full thing. I can just import this if I wanted to. However, I am considering here, since Haskell is a lazy language, will this function import all of them? Or will the actual functions just get imported when we use them? Oh wow, that was a mess. That was an annoying song. Not annoying, but it really took attention. Geometry has to be the same folder that the program that's importing it is in, though. It has to be in the same folder or it has to be linked to it. But yeah, for our sake, it's probably the best way to just have it in the same. You can probably make a library or whatever. Right, we have been importing stuff that was not in the same folder, so we know that we can do it. Node owner says, that was a classic Pokemon song. This is too? I didn't know that. I mean, it's not necessarily a bad song, it was just bad for my use case right now. Modules can also be given a hierarchical structure. Each module can have a number of submodules and they can have submodules on their own, off their own. Let's section these functions off so that geometry is a module that has 3 submodules, one for each type of object. Oh, you have to do submodules. Maybe that's... I thought we imported just functions, but maybe we have been importing submodules. Right, first we'll make a folder called the geometry. Mind the capital G. Yeah, the G and then a spot. Yeah. In it, that's a few punctuation, that mark. Is this just called a punctuation mark? The literal Swedish word is a spot. Yeah, so it's in Swedish this looks like a G spot, which is funny. Yeah, I thought that was funny anyway. In it we'll place 3 files: sphere, cuboid, and cube.hs. Alright, so we just make or a module can be a directory, it doesn't have to be a file. Right, sphere.hs. Yeah, exactly, we just split up our functions in submodules. This makes sense. And I understand why people would want to do that. Right, we just do the same thing, but they all, like, the cuboids get their own file, the cubes get their own file, and the spheres get their own file. I wonder, did they remove the rectangle? They probably removed the rectangle, right? No, the rectangle is still right here for the cuboid. Oh right, they only used them in the cuboid. They didn't use them in the cubes. Oh, actually they imported. That's kind of a mess, isn't it? We made a cube and we import cuboid. I mean, I assume, yeah, we're just doing it to show that this can be done, but doing it this way seems like, yeah. And, well, I guess we learned that we can import a like if we have 3 submodules, we can import one of the submodules into the other submodule. I wonder what happens if we, right, since we import these, what happens if we try to, in our cuboid, try to import cube? Will we just end up in... No, since it's a lazy language, we will not end up in an infinite import thing. Assuming that the import works lazily as well. I think that's a fair assumption to make. Yeah. Right. First is geometry sphere. Notice how we placed it in a folder called geometry. And then we defined the module name as geometry.sphere. We did the same for the cuboid. Also notice that how in all 3 submodules we defined functions with the same names. Yeah. We can do that because they're separate modules. Oh, I didn't pay attention to that. We want to use functions from geometry.cuboid and geometry.cube, but we can't straight up import it because it has the same names. We have to do a qualified import. Right, sure. Now, if we're in a file that's on the same level as the geometry folder, we can do say import geometry.sphere. Oh, that's our data.list and our data.char that we have been importing. Data.list or data.sphere. That makes sense if we make this big modules. And then we'll call area and volume, and they'll give us the area and volume for a sphere, yeah? And if we want to juggle 2 or more of these models, we have to do qualified imports because they export functions with the same names. So we just do something like, boom. And then we call sphere.area, sphere.volume, cuboid.area, etc. And we'll calculate the area or volume for their corresponding objects. Right, I gotta say that when we first started learning about importing stuff, I was like, why did they name it the same names? But it makes a lot of sense because you kind of build your own modules and whatnot. And just because something is named something in one module, that's not an argument for it not being named the same thing in another module, because you end up in an infinite regress, right? Where every name you ever figure out can't have the name as something else within the Haskell infrastructure, right? And that's a mad restriction to put on anyone. No, you want to give the best name you can. I'm terrible at naming conventions, so but that doesn't matter. You want to do good naming. Use words good, yes, exactly. The next time you find yourself writing a file that's really big and has a lot of functions, try to see which functions serve some common purpose. Then see if you can put them in their own module. You'll be able to just import your module the next time you're writing a program that requires some of the same functionality. That is definitely a benefit. Wait, is this making our own types and type classes? Oh. Next is chapter 9. Not yet. Making our own types and type classes. That's what's next, eh? Own types as well, eh? That's interesting. In the previous chapters, we covered some existing Haskell types and types classes. We did. In this chapter, we'll learn how to make our own and how to put them to work. Algebraic data types intro. So far, we've run into a lot of data types. Bools, ints, chars, maybes, etc. Right, the maybe was a data type. But how do we make our own? Well, one way is to use the data keyword to define a type. Let's see how the bool type is defined in the standard library. Data bool is either false or it's true. So we could make our own bool where we just say F for T. So we don't have to type it out. Or if you want to use, instead of using capitalized letter, you could use just normal letters. Normal, tiny letters. Whatever they're called. Lower, upper, yeah. Data means that we're defining a new data type. That is it, alright. The part before the equals denotes the type, which is bool. The parts after are value constructors. They specify the different values that this type can have. The pipe is read as OR. So we can read this as the bool type can have a value of true or false. Both of the type name and the value constructors have to be capital case. Much do you want to bet that int is 0-9? No, that doesn't even work either. That would just be... Is it defined as an infinite list? 0 ... But it can, an int can be negative as well, can't it? It has to be defined as an infinite list though. Can we do ... 0 ... No, wait, int has a lower and yeah, it has a max and a min value, so it's probably the min value ... to the max value. Wait, here we go. It ain't. It's either... Wait. Oh, right, yeah. Wait, no. Either it's 2147483648, 2147483647. Why would you define both of these? Oh, right, to know the step count, right? We have to know the step count. That's why you take both of them. You take the lowest and then the second lowest, then we do the ... Why do we define the middle? And then we define the end. I wonder why this is here. We can think of the int type as being defined like this. Oh, because we switch over from the negative to the positive and we kind of want to denote what is happening. And just make sure that... The first and last value constructors are the minimum and the maximum possible values of int. Yeah? It is not actually defined like this. The ellipses are here because we omitted a help load of numbers. So this is just for illustrative purposes. Oh, so it is actually defined with all the numbers in mind? You don't use the ... Huh. Now let's think about how we could represent a shape in Haskell. One way would be to use tuples. Circle could be denoted as... where the first and second fields are the coordinates of the circle's center and the third field is the radius. Okay, sounds okay, but you could also represent a 3D vector or anything else. A better solution would be to make our own type to represent the shape. Let's say that a shape can be a circle or a rectangle. Wait. The shape can be a circle or a rectangle. So shape can be circle, float, rectangle, float. Yeah, I'm a little bit confused. Right, so now what's this? Think of it like this. The circle value constructor has 3 fields, which takes floats. So what, the shape is just a collection of shapes? And then we have, oh, it can either be a circle, float. Yeah, so it's like a metadata type, right? These data types are just, they are basic. They are the basic building blocks of data. But this data type is built off of other data types, I guess. When we write value constructor, we can optionally add some types after it, and those types define the values it will contain. Here, the first 2 fields are coordinates of its center, and the third one is its radius. Okay. The rectangle value constructor has 4 fields which is accept floats. The first 2 are the coordinates and to its upper left and corner, and the second 2 are coordinates to its lower right one. Yeah. Okay. So we always have to put a name, but right, the name of the 0 int is a 0, right? Just like the name of 1 is 1. This is the representation of our data. So this is the representation of our data, but this is the actual data. Yeah, representation content, if you want to call it that way, yeah. Okay, now when I say fields, I actually mean parameters. Okay, value constructions are actually functions that ultimately return a value of a data type. All right, I was kind of thinking that. Circle function. Wait, could we return the circle? Let's take a look at the type signatures for these 2 value constructors. Type circle, it's a... Yeah, exactly. It returns a shape. And the shape is a circle or it's a rectangle. Oh, actually it says here. That's a circle or a rectangle. Cool, so value constructors are functions like everything else. Who would have thought? Let's make a function that takes a shape and returns its surface. Hello, Cole, get in on tap. Nice to see you again. Oh shit, I forgot to start the bot today. I hadn't noticed until right now. Oh shit, not like that. Right. Now we're up and running, calling it in on tap. If you wanted some inspiration, that is. Wonder what category I was looking under. Right. Remember that the king of yoga once said, you gotta have at least some respect for a message. The king of yoga, eh? Some respect for a message? Man, I think that our generation has kind of forgotten how important messages were, right? There were people who had as a job just to get up on a horse and write a message from one side of a country, right? They could ride all day with one message. Just took a piece of paper that was stamped and, man, so much respect. And in war times, right? You had archers just to shoot down. They trained pigeons just to send messages back and forth. Yeah, I think I do have. They had archers to shoot down all the pigeons. It's kind of cool. Outrunner says that there's an enemy called Jabber in Levelhead, and the description is, just wants to have a really boring conversation. Nice. Jabber. Like that. Right. Cool, so value constructors are functions like everything else, if we're getting back to it. Who would have thought? I was kinda guessing, but let's make a function that takes a shape and returns its surface. Right, surface, it takes a shape and returns a float. Oh, right. And then we just pattern match. If we have a circle, this is our surface. If we have a rectangle, alright, we define which of the values that we do need. Yeah. abs again. Will this help if I just do T abs? I don't think you can see this. I'm in the way. Oh, you can see it. It's right there. Right there. You can see it. A bit little, small maybe. I don't know. Right, that doesn't help. It takes the absolute value, right? If we do abs -5, no. 3.4. No? I don't remember. Colgatino Tab says, I missed early stream. Have you made your own types yet? I mean, kinda, right? We did just do these. The shapes and the rectangles. We learned how to do ints, and we could make our own bools. We haven't, I mean, I haven't made any myself because it's pretty straightforward so far. We just used our circle and our rectangle to calculate the surface. Right, here is where we get to the point where we see the value of creating our own types. Because types can be used to pattern match, right? Even though they are functions. Wait, why? Why do we define them as data, by the way? Can't we just have the function? No. Because, yeah, exactly. Defined, it's yeah, they are, you use them a little bit differently, right? A type can be used as a parameter. Functions can be used as parameters as well, but I guess it becomes more readable. Right, the first notable thing here is the type declaration. It says that the function takes a shape and returns a float. Yeah. We couldn't write a type declaration of circle to float because circle is not a type. Shape is. Just like we can't write a function with a type declaration of true into an int. The next thing we notice here is that we can pattern match against constructors. Yeah, exactly. We pattern matched against the constructors before all the time, actually. When we pattern matched against values like an empty list, or false, or 5, only those values didn't have any fields. We just write a constructor and then bind its fields to names. Because we're interested in the radius, we don't actually care about the first 2 fields, which tells us where the circle is. Indeed. NodeRunner says in Levelhead he's building a level and he doesn't know if he can beat his own level to publish it. Well, that's a problem. Right? Either you spend a couple of... If you know that it is beatable, spend a couple of hours, right? Ooh, I wonder, is it doable? Bit low, isn't it? Do we hear the music? Yeah, I was thinking. It's a file, right? So you can probably send the file to someone else who could beat it. If you know someone who has the game and is good at 2D platformers. I was gonna offer, but I think you're better than me on platformers. So if you can't beat it, maybe I can't either. Well, Getino Tab says, can you get someone else to beat it for you? However, a big problem with that, I don't think I can beat the level. Well, let's assume that I was good at platformers, which I'm not. But let's assume you sent it to me, I beat it. Then I would have published it. So, I guess the only way to have someone beat it for you, that would be sharing your password with them. Yeah. Too bad I don't know anyone else with this game. Alternative is get good. or make the level easier. But yeah, get good Node Runner. I mean, you could just wait. You don't even have a password. Well, right, the way the login works is you give an email, right, and you just press accept. You get an email when... So yeah, you could have someone else help you out by using your login and then beat it for you with that login. But yeah, you would have to know someone who was good at the game to help you do that, and that you trusted with the login, right? They could probably continue... Well, actually, they don't even have to own the game, do they? They just need a download, and then they can log in and play it with your account, because you own the game. Then again, if they don't own the game, they're probably not gonna be good enough to beat the game for you. Decisions. Alright, because we're interested in the radius, we don't actually care. Yeah, exactly, we don't care. And then we just call surface. Right. And we just define our data type. That's where I got confused. We had our from list before, right? That's part of our data type. From list is part of our data type. A little bit weird, but you can get used to it, I guess. Node owner says, I'll just use this chance to improve it further. Yeah, exactly. You gotta test the level, right? And if you made it difficult, you test how it feels to be bad and playing it over and over and over again. Maybe you had one too few checkpoints. Maybe that is part of the level. Because you get stuck in some place and just have to stay there for hours. I don't know. Yay, it works. But if we try to print out circle 1025 in the prompt, we'll get an error. Really? That's because Haskell doesn't know how to display... Oh, right. We haven't told Haskell how to display it as a string yet. When you print stuff, you only print strings. We've gotten errors like that. Similar errors before, I think. Remember when we try to print a value in the prompt? Yeah, exactly. Haskell first runs the show function to get the string representation of our value and then prints that out to the terminal. To make our shape type part of the show type class, we modify it like this. Just gonna answer this message real quick. Right. Oh. Man, I'm looking forward to, in like a year or so from now, I'm gonna probably be an owner of a PinePhone Pro. I'm really looking forward to that. Maybe a little bit less than a year. I think like in the middle, like probably in summer it shows up. This. Okay, Tinotab says, nice, having respect for that message and replying to it. Yeah. Showing respect. Replying. Are we good with the music? I think we're fine. Right, we modify it by having this, and then we're deriving show. So does that mean... Wait. No? I did not meant... Show is a function. No, I meant the data type. Right, we don't concern ourselves with deriving too much for now. Oh, yeah, we won't. Sorry. Let's just say that if we add a deriving show at the end of a data declaration, Haskell automatically, nice, makes it part of the show type class. So now we do this. Magic! Show is a type class, not a data type. Right. That was my confusing thing. Yeah, it's not a data type, it's a type class. I've been confused by that before. Is there a way to list all the types of a type class? Right? Like if I wanted to show, right, if I wanted to list out in here in GHCI, let's say I wanted to show all the data types that are part of the num type class. Is there a way to do that in here, or would I have to go to a browser and search for it? Do you know, Colgate on tap? Right, so now we can do this. Boom, we can write them out and they will be printed. Colgate on tap doesn't know. Maybe we'll figure it out. Right, that's something I wanted to. I mean, part of me wants to have all the help in the GHCI, right? Part of me wanted to have definition of functions, right? Sure, we can show the type of the show function, but could we get a description? Actually, we can do help, right? Actually, let me do this in full screen, and what do we have? We can do quite a few things in here. Wow, quite a few things. Here we go. We can evaluate a statement. We can repeat the last commands. We can make a multi-line command. Wait. We can add modules. We can browse, display the names of defined by module. So if we do browse prelude, oops, that work? It does work. And we get all the stuff in prelude. Oh man. I'm assuming we don't have a grep in here. What is happening? I guess we can live with this. Music is a little bit weird. Right, we have a lot of things in here. Right, we get all of those functions. We get type, and we get data. Oh, so this is like a declaration line of the data type pair. Type double and then the data dot double, right? Yeah. Which part of type class is it? No, wait. Very weird. This is from a game called Friday Night Funkin'. Great game. Haven't heard of the game. Alright, so we can do this. Even though there is no grep, but maybe there is a grep. We don't know yet. What else do we have? Where were we? We got browse. We got change directory. Look at that. Wait, run the command returns by expression. Okay. Actually, I wonder if we can run other stuff. Well, get in on tap asks, how did you do that? Which one? This one is just :h for help. That's usually how it is, right? I just did :h. But then I did browse. Display the names of defined by module. And since we're in the module prelude, I just defined, I browsed everything that was part of prelude. What else do we have? Complete. List completions for partial input strings. Don't understand what that is. Neat? Yeah, right. Very neat. Got define command. Okay. Displays docs for the given name. Experimental. Ooh, that one is what I was looking for, I think. So if we do I wonder if it, like, doc... Is it doc num? Basic numeric class. The Haskell reports define no laws for num. However, plus multiplication are customarily expected to define a ring and have the following properties. Hey. This doesn't super help me, but we did get some documentation on it. Algebras is calling. Oh, it's maths. Right, what I should have done was doc show. Specialized variant of show rec using precedence context 0 and returning ordinary string. So what is show precedent? Oh. Shows. Where are we? Convert a value to a readable string. There we go. Should satisfy the law, and then you have a law here for how it works. I'm just gonna do, can we just do D? Can we just give it the D and it'll be happy? Yeah. Wait, is it the same? No. Doc is a little bit different. D was different as well. So what was just a normal D? What if we open H for help? Alright. Colgate Inner tab shows us a link to ring mathematics. Do I have to? Do we have to look into this? I know how I feel about mathematics. In mathematics, rings are an algebraic structure that generalize fields. Multiplication need not be commutative, and multiplicative inventives need not exist. In other words, a ring is a set equipped with two binary operations satisfy. You've already lost me. If anybody's interested in rings, here you go. It's probably valuable information in this. But I think we've been sidetracked enough. Haven't we? Yeah, sidetracked enough. Where were we? Right, yeah, if we make them to be derived by show. Alright. Good thing to know in the GHCI that the help function, there is a lot of stuff you can do in there probably that is very helpful. Surprisingly. Value constructors are functions, so we can map them and partially apply them in everything. If we want a list of concentric circles with different radii, we can do this. Map, circle, and then on a list of things. Huh. Oh, yeah. That is gonna confuse the shit out of me. This is a function, but it's also an unfinished data type. Oh man. That makes my head spin just hearing it. Like, why do we have data types and functions if data types are just functions? Makes my head spin. Right. Our data type is good, although it could be better. Let's make an intermediate data type that defines a point in a two-dimensional space. When we can use that to make our shapes more understandable. Right, we make a point, which is a float and a float, and it's a deriving show. That makes sense. Can't we derive num as well? No, we don't have to because it's a float. We don't have to derive num because, well... Right. Data.shape, it's a circle point float. Okay. Rectangle is 2 points. Okay. Notice that when defining a point, we use the same name for the data type and the value constructor. This has no special meaning, although it is common to use the same name as the type, if there's only one value constructor. Shit, I'm getting tired. I wasn't listening to this sentence at all. I'm sorry, I'm just gonna repeat this one more time. Notice that when defining a point, we use the same name for the data type and the value constructor. Oh, we did, yeah. Because we only have one point. We only have one. There is no or. This is a point. This is how you do a point. I'm assuming. This has no special meaning, although it's common to use the same name as the type if there's only one value constructor. Yeah, exactly. So now the circle has two fields. One is of type point and the other of type float. This makes it easier to understand what's what. Same goes for a rectangle. We have to adjust our surface function to reflect these changes. Yeah, exactly. Right, I kind of like the way we're supposed to be thinking in Haskell, right? Split everything up. Let every line do one thing. Right? We could have a rectangle and a circle by themselves, but it would be much better to have a point. Because we do use a point, so we split them up and we use a point. It's very much going down to the basics of what's going on. Right, the only thing we had to change were the patterns. Yeah. We disregarded the whole point in the circle pattern. In the rectangle pattern, we just used a nested pattern matching to get the fields of the points. If we wanted to reference the points themselves for some reason, we could have used as patterns. Yeah, exactly. Wait. Oh yeah, surface. Missed out that. It's a rectangle and we have the points and those points. And we get surface area. Exactly. How about a function that nudges a shape? It takes a shape, the amount to move it on the x-axis and the amount to move it on the y-axis, and then returns a new shape that has the same dimensions, only it's located elsewhere. Nice. Alright, so we do have nudge a circle. We have all these things. Right, we have our circle. This is our circle. Then we take AB. Wait. Takes a shape and moves it on the x-axis, the amount to move it on the y. Oh, right. We move it on the x-axis and we move it on the y-axis. Right, of course. I was like, why do you need two numbers? I was just thinking about moving in the x-axis, but of course we want to move in the y-axis as well. Or it should be possible to nudge it. I mean, you could. AB is nudge amount. Yeah, but in different dimension. X and Y, yeah. So, wouldn't it be the Haskell way to just, if we're going to the extreme, to have one function to nudge it on the x-axis and another function to nudge it on the b-axis? Well, actually, that is what we have here because of curried functions. That's what we have. Nudge on the x-axis, nudge on the y-axis. That's why that's what we have. We have two functions in here already. And the same with this. Yeah. Pretty straightforward, yeah. We added nudge amounts to the points that denote the position of the shape. Indeed. We nudge it. If we don't want to deal directly with points, we can make some auxiliary function that creates shapes of some size at 0 coordinates and then nudge those. Auxiliary functions. Base circle. Wait, I'm confused. What are we doing? Right, float into a shape. Okay, so we have the base circle and we have our float here. Oh. Oh, okay. We're just creating extra circles. And nudging those for whatever reason. You can, of course, export your data types in your modules. Yeah, to do that, just write your type along with the functions you are exporting and then add some parentheses and in them specify the value constructors that you want to export for it, separated by commas. If you want to export all the value constructors for a given type, just write ... If we wanted to export the functions and types that we defined here in a module, we could start off like this. Alright, modules, shapes. We have point ... that means all the value constructors. Point ... shape ... and then all our functions. By doing shape ... By doing shape ... we exported all the values constructors for shape. Yeah, so that means that whoever imports our module can make shapes by using rectangle and circle value constructors. Yeah, it's the same as writing shape, rectangle, circle. I feel like it's falling to place, right? Like a couple of days ago, we learned about the from list data type, and that was super confusing. But here, when you look at how it is actually, how you construct a type in Haskell, it makes a lot of sense to have this. This is, wait. And this is what a point looks like. Point 60.023 but 0. This is a point data class. Data type, sorry. Yeah, this is a data type. And that gives me, the user, a very easy interface to make my own data types if I would need to, would want to. Wait. You can use it by rectangle and circle. Yeah, it's the same as writing shape, rectangle, circle. Exactly. ... means just all of them. All of them. We can also opt not to export any value constructors for shape by just writing shape in the export statement. That way, someone importing our module could only make shapes by using the auxiliary functions base circle and base rect data.map uses that approach. You can't create a map by doing map and then do this, because it doesn't export that value constructor. However, you can make a mapping by using one of the auxiliary functions like map from list. Remember, value constructors are just functions that takes field as parameters and returns a value of some type, like shape, as a result. So when we choose not to export them, we just prevented the person importing our module from using those functions. But if some other functions that are exported return a type, we can use them to make values in our custom data types. Not exporting the value constructors of a data type makes them more abstract in such a way that we hide their implementation. Also, whoever uses our module can't pattern match against the value constructors. Outlander says the level was shipped. Oh, nice. I'll play that tomorrow. The shipped level. Right. Not exporting the value constructors of data types make them more abstract in such a way that we hide their implementation. Also, whoever uses our module can't pattern match against the value constructors. Why wouldn't we want that? Oh, right. If we... we can create specific types that only we want to use. Just like we use helper functions, we can use helper types to make our modules easier to work with. All right. Guess that's enough Haskell for today. And we'll continue that tomorrow.